Hi everybody, we're starting the limits unit now. So if you could please make sure you have printed out a blank copy of the limits notes. I'm going to go through them as best I can, and then remember that there's a filled-in copy of the limits notes also as a link on Schoology that you can use to fill this in. So I need to start off by saying a limit is a y value. You've always got to keep in mind that it's a y value and it's a location. So on your graph, if you think of a graph and the y value of a graph, that's what your limit would be if it exists. And sometimes it doesn't. So I'm going to go through these first three examples in your notes. The first example is, oh, and by the way, for limit notation, it's written as the limit as, and you say as x approaches 2. Sometimes there's a line in there that it looks more like a fraction, and sometimes there's not. Either way, it's the limit. For this one as x is approaching 2. And what you have to do when you're considering a limit is look at your function as x approaches 2 from both the left and the right, and then you have to see the y values as x is approaching 2 from the left and the right. So here's a picture of the function. As x is approaching 2 from the left, my f of x, my y value, remember a limit is a y value, my y value is approaching positive 2. As x is approaching 2 from the right, my function, my y value, is approaching positive 2. Because as x is approaching 2 from the left and the right, and our y values are coming to the same point or the same location, there's a limit, and the limit is that y value. So in this case, the limit is a y value of 2. For example number 2, there's this parabola, and we're trying to evaluate the limit as x approaches 0. So we've got to look from the left and the right to the graph. As x is approaching 0 from the left, your y value is your limit. Your y value is approaching a y value of negative 1. As x is approaching 0 from the right, my function, my y value, is also approaching negative 1. Now, it's clear from the graph that at an x value of 0, there is no y value. The function's undefined right there. But because the y values are coming to the same location from both the left and the right, there's a limit. So the function doesn't always have to exist for a limit to exist. As long as those y values come to the same point for a certain x value, a limit exists. And in this case, it's a y value of negative 1. For the third example, we're going to look for the limit as x approaches 1. So here's where x is a positive 1. When you're looking as x approaches 1 from the left, your function value, your y value, is approaching a y value of 2. When I'm looking as x approaches 1 from the right, my y value is approaching a y value of negative 2. And when I look from the left and the right as x is approaching 1, my function is not coming to the same y location. In this case, the limit doesn't exist. Unless it comes to the same y value from the left and the right, there is no limit. And when a limit doesn't exist, we use the abbreviation DNE for does not exist. Now, example 4 and 6 are going to be calculator questions, and I'm going to do 4 and then 6, and I'll go back and pick up example number 5. So for example number 4, if you're evaluating a limit algebraically, you can use your graphing calculator. So for this, we're looking for the limit of this function as x approaches positive 1. So what I did is I set up a chart with values that are less than 1, getting closer and closer and closer to positive 1, that are greater than 1, getting closer and closer to positive 1. So if we were looking at this on a graph, this would be our x values getting closer to 1 from the left. This would be our x values getting closer to 1 from the right. Now there's a way to do this on your graphing calculator, and I'm hoping that you can see what I'm doing. Okay, so what we're going to have to do is we're going to use our stat key. Let me make sure I can have this kind of right in front of you. We're going to use our stat key and hit edit. Okay, now I have information in my list right now, so the way you clear a list is you arrow up. So L2 is highlighted, hit clear and enter, and that'll clear out that list. I'm going to do the same thing for my list 1. I arrowed up, I hit clear, and then enter, and now I have 2 cleared lists. Now, those x values we're going to enter into L1. So you would type each one in, hit enter in between. So I'm going to enter 0.8, hit enter. I'm going to enter 0.9, hit enter. 0.99, enter. 0.999, enter. An x value of 1, enter. So here's how my list looks so far in L1. Keep going. 1.0001, enter. 1.001, enter. And 1.01, enter. So what I've done is I put all of those x values into my L1. Now, I want the calculator to figure out all the corresponding y values in one step. So what we're going to do is we're going to enter the equation that we're finding the limit of into L2. And the way that you do this is you arrow over to L2, arrow up so L2 is highlighted, and hit enter. And it's going to bring your cursor down to the bottom. It's blinking and it says L2 equals. And what we want to do is we want to use all of those L1 values at the same time. So when we type in the equation, instead of typing in x squared minus 4 divided by x minus 2, I want all my L1 values squared minus 4 divided by all of my L1 values minus 2. So because the top and the bottom are both binomials, I need to start with a set of parentheses. I want my L1 values. My L1 is above the number 1, so I'm going to hit second with my number 1. Do you see how it says L1? I want all of those values squared, minus 4, close the parentheses for the numerator, and now I need to divide those by opening a parentheses for the denominator, all of my L1 values that I've typed in. So second above the 4 is my L1, minus 2, close the parentheses, and when you hit enter, it's going to calculate all of those y values. So when I look at those y values, I have a y value of 2.8, and then I have a y value of 2.9, 2.99, 2.999, and then here I have a y value of 3, and then a y value of 3.0001, 3.001. Gotta go down 1 to get the last y value, and my last y value is 3.01. So from this table, I'm going to evaluate the limit of this function as x is approaching 1. As x is approaching 1 from the left, my f of x, my y values are getting closer and closer and closer to positive 3. Actually, they come right to positive 3. As x is approaching 1 from the right, my y values are coming to a y value of 3. Because the y values are coming to the same location from both the left and the right, the limit exists, and the limit of this function is a positive 3. Now I'm going to do example number 6 next. I'm doing this next because I needed to have this table up here to do this video. So what I need to do is I have to clear out my lists. So I'm going to hit my Stat, Edit, Highlight, go up to L2, hit Clear and Enter. Do the same thing with L1, highlight L1, clear and enter. So now I have a cleared calculator. I'm going to put all of these x values into my L1. In this case, though, if we're looking for the limit as x is approaching 2 from both the left and the right, if I had an x value of 2, I would have a 0 in the denominator, so it would make the function undefined. So in this situation, we can't include this x value of 2 in our list, or it's going to give us an error message. So I'm going to put everything except that x value of 2 into my list. So in my L1, I'm going to start with 1.8, enter, and then I need 1.9 and 1.99, 1.999. I'm not going to include my x value of 2 because it would make the function undefined. Then my next x value is 2.0001, enter, 2.001, enter, 2.01, enter. So there are all of my x values in my L1. I want the calculator to figure out all of the y values at the same time. So I'm going to put my equation in for L2. So I'm going to arrow over, highlight L2. So I use my up arrow key. The L2 is highlighted. Hit enter. And then my cursor's down on the bottom of my screen and it's blinking. And I'm going to type the function in. But instead of typing in x squared plus 4 divided by x minus 2, I want to choose all of my L1 values. So start with my parentheses. All of my L1 values squared, remember that's second above the number 1. All of my L1 values squared plus 4. Close parentheses, there's the numerator of the fraction, divided by all of my L1 values, so parentheses to start my denominator. My L1 values is second above the number 1. My L1 values minus 2. And when I hit enter, it's going to give me these corresponding y values. Okay, so when x is 1.8, my y value is negative 36.2. When x is 1.9, negative 76.1. When x is 1.99, negative 796. 1.999, negative 7,996. Okay, when x is 2.001, I've got 80,000, 004, 80,004, and then 8,004, and 804.01. Okay, so there's my corresponding y values. So, as x is approaching 2 from the left, my f of x, my y values, are getting smaller and smaller and smaller. So they're going to negative infinity in the y direction. As x is approaching 2 from the right, my x values are getting bigger and bigger and bigger and bigger. So from the left, my y values are going to negative infinity. From the right, my y values are going to positive infinity. That means they're not coming to the same y value. So in this case, the limit does not exist. And if you look at the graph of this function, which I've already put in here, it justifies it. So as x is approaching 2 from the left, my y values are going to negative infinity. As x is approaching 2 from the right, my y values are going to positive infinity. So at an x value of 2, the y values are not converging on the same location, so the limit doesn't exist. Now I'm going to go back and do example number 5, which is an algebraic method. So for example number 5, we're evaluating the limit as x approaches positive 2. Now remember what I said, sometimes there's going to be a line in here and it'll look more like a fraction whether the line is there or not there, it's still a limit. So what is the limit as x is approaching positive 2 of the function x squared minus 4 divided by x minus 2? Now, I know immediately that x cannot be a positive 2 because it would make my function undefined. It would give me a 0 in the denominator. So x cannot equal 2. That doesn't mean that the limit doesn't exist. All right, so we're going to do this by direct substitution. First, we're going to simplify the function. So for this one, we're looking for the limit as x is approaching positive 2. The numerator adopts factoring x plus 2, x minus 2 divided by x minus 2. We have to remember that x cannot equal 2. When we simplify this, the limit as x is approaching 2, now it simplifies to be x plus 2. Now, even though I know that x cannot equal 2, if you think back to when we did the derivative with the limits, the derivative by definition, and after we evaluated the difference quotient, and then we substituted h with 0, and we dropped it out of the equation at that point, I've simplified the function as much as I can. So at this point, I'm going to go to direct substitution and substitute 2 in for my x. So I'm dropping out the limit because my function is simplified. I get 2 plus 2. I've replaced that x with this 2. So the limit is 4. So what I'd like you to do for this one is now I'd like you to pick up your calculators. I'd like you to type this into your y equals screen and type in the x squared minus 4 in parentheses divided by x minus 2 in parentheses. And do just zoom 6 and look at the function, and it absolutely looks like it's a continuous function. But if you go to your table, you'll see that there's an error message at x equals 2. So this is called a point discontinuity. So as this function is approaching 2 from the left, the y value is approaching a y value of 4. As it's approaching 2 from the right, the y value is approaching a y value of positive 4. So even though the function is undefined at x equals 2, there's still a limit. And it's a lot like this example right here where there's just a little hole in the graph. So I hope that helps you to understand limits day 1. Tomorrow I will have your homework answers posted, and I think I'm going to try to do a video talking you through the homework too. So I hope you're well, and I look forward to talking to you all soon.